Today we're going to talk about request smuggling in WebSockets, which is a part of TryHackMe's web app pen testing. In today's room, we'll look at ways to smuggle requests through proxies by abusing WebSockets. The learning objectives is to understand how WebSockets work, learn how to exploit HTTP request smuggling via the WebSockets functionality, and learn how to use tools to detect and exploit this vulnerability. Before we dive into this room, I just want to make sure that you get the basic understanding of HTTP request smuggling. If you haven't done so, you can visit this room, HTTP Request Smuggling. This provides you with basic information about this vulnerability. Now without further ado, let's get started. So what is a WebSocket? When using HTTP, the client must make a request before the server can send any information. This complicates the implementations of some application features that require bidirectional communications. For example, suppose you are implementing a web application that needs to send real-time notifications to users. Since the server can't push information to the user at will, the client would need to constantly poll the server for notifications, requiring lots of wasted requests. The WebSockets protocol allows the creation of two-way communication channels between the browser and the server by establishing a long-lasting connection that can be used for full duplex communications. Upgrading HTTP connections to WebSockets. The WebSocket protocol was designed to be fully compatible with HTTP. Establishing a WebSocket connection follows a process similar to that of H2C. The client sends an initial HTTP request with an upgrade WebSocket header and other additional headers. If the server supports WebSockets, it responds with a one-on-one switching protocol's response and upgrades the connection accordingly. From that point onwards, the connection uses the WebSocket protocol instead of HTTP. So over here, if you take a look at the request, we see the response is one-on-one switching protocols, which indicates a successful upgrade. If we now add a proxy in the middle, something interesting happens. Instead of fronting the connections themselves, most proxies won't handle the upgrade, but will instead relay them to the backend server. Once the connection is upgraded, the proxy will establish a tunnel between the client and the server, so any further WebSocket traffic is forwarded without interruptions. The problem we now face is that the tunnel uses the WebSocket protocol instead of HTTP. If we were to attempt to smuggle an HTTP request using this tunnel, the backend server would reject it, as it expects WebSocket's request. Answer the question: which status code signals a successful WebSocket upgrade? 101. Abusing WebSockets for request smuggling. To smuggle requests through a vulnerable proxy, we can create a malformed request such that the proxy thinks a WebSocket upgrade is performed, but the backend server doesn't really upgrade the connection. This will force the proxy into establishing a tunnel between the client and server that will go unchecked, since it assumes that it is now a WebSocket connection, but the backend will still expect HTTP traffic. One way to force this is to send an upgrade request with an invalid set WebSocket version header. This header is used to specify the version of the WebSocket protocol to use and will normally take the value of 13 in most current WebSocket implementations. If the server supports the requested version, it should issue a one-on-one switching protocol's response and upgrade the connection. But we aren't interested in upgrading the connections. If we send an unsupported value of the WebSocket version, the server will send a 426 upgrade required response, indicate the upgrade was unsuccessful. So now we have two status codes to look at. One-on-one switching protocol, meaning that the connection has been successfully established. 426 upgrade required response indicates that the upgrade wasn't successful. Some proxies may assume that the upgrade is always completed, regardless of the server's response. This can be abused to smuggle HTTP requests once again by performing the following steps. First, the client sends a WebSocket upgrade request with an invalid version number. Second, the proxy forwards the request to the backend server. Next, the backend server responds with a 426 upgrade required. This connection doesn't upgrade it, so the backend remains using the HTTP route switching to a WebSocket's connections. And last, the proxy doesn't check the server response and assumes that the upgrade was successful. Any further communications will be tunneled since the proxy believes they are part of an upgraded WebSocket connection. Now, it is important to note that this technique won't allow us to poison the other users' backend connections. We will be limited to tunneling requests through the proxy only, so we can bypass any restrictions imposed by the frontend proxy. Let's check the applications at port 8001, the flag directory. This application is running behind a varnished proxy with a vulnerable configuration. Our objective in this application is to retrieve the value we store in the flag directory. As a first attempt, if we try to access the flag directory, we are presented with the following error message: 404 not found. Now, this may seem like a regular 404 error, but when we try another one, which is non-existent 134, the error message presented will be different. At this point, we should be suspicious that the frontend proxy is restricting access to the flag directory in the backend server. Luckily, there's also a WebSocket endpoint we can abuse at /socket. Let's try to send the following payload to smuggle a request for the flag inside the directory. And this is going to be the payload. To send a request, we use Burp's repeater. To ensure Burp doesn't modify our request and break the attack, we need to make sure that the update content length setting is disabled. Once this is done, we can send our payload and should get a flag. Also, make sure that there are 2 new lines at the end of the payload, which is right here. So the response will be, the first response is 426 upgrade required, which is expected because we want it to fail. And then the second one is going to be the response of our smuggle request, which is get flag. And here's going to be the flag value. So let's try that. I'm going to copy the IP address of the target machine. $67 $175.51. Okay, that's correct. Okay, here we have an error 404 not found. Let's try something else, and we get a different 404 error message. Now we can try to smuggle this request. We have a socket right here. Turn on Burp intercept, and then send this request. Burp is going to capture this one. We send it to a repeater, and over here we try the payload, which is this one. Now we have to make sure that everything is correct. First, make sure that there are 2 new lines at the end of this payload. Second, we have to disable this one, update the content length. Third, let's make sure that any other information is correct. This is the host, port number, the flag, invalid WebSocket version. We should be good. So let's send it. And here we go. We get a flag. The first response is 426 upgrade required, and the second one is 200. Okay. So we have successfully bypassed the proxy restrictions to get the flag value. Now we're going to copy this one and paste it into the answer. What if the app doesn't speak WebSocket? Some proxies will not even require the existence of a WebSocket endpoint for this technique to work. All we need to do is to fool the proxy into believing we're establishing a connection to a WebSocket, even if this isn't true. Look at what happens if you try to send the following payload, be sure that we have 2 new lines at the end of payload. This payload should still work even though the first request is directed to the home page, which is not a WebSocket endpoint. The proxy simply doesn't check the response from the upgrade, so you now can't use any payload that looks close enough to the WebSocket upgrade. So here, instead of WebSocket endpoint, we can just try any other directory, and when we tried it, it should work. Okay, so looks like it doesn't work. That's okay. This payload will randomly fail using Burp. You can either try the payload a couple of times until it works, or deliver it by pasting that into the command running the netcat command, where it will work every time. Let's try copy this one more time. This is the IP address. No. Let's copy this one. It's not working. There we go, we get a flag. So obviously we're gonna have to try several times to make sure that it works. Moving on, defeating secure proxies. So far, we've been working with a proxy that won't check the web server's response to determine whether the WebSocket upgrade was successful. In this task, we replace the vulnerable Vanish proxy with an Nginx proxy that checks responses before tunneling requests through a WebSocket connection. The backend application still have the socket endpoint, with the WebSockets and the flag endpoints as our target. The new application can be accessed on port 8002. When we first try running the payload we used in the previous task, we're going to get a 426 upgrade required, and the backend server doesn't show any flag. The Nginx won't leak despite getting a 426 response for the initial WebSocket upgrade attempt. Since Nginx is checking the response code of the upgrade, it can determine that no valid WebSocket connection was established. Therefore, it won't allow us to smuggle the flag request. Tricking the proxy. Since we can't just smuggle requests anymore, we need to find a way to trick the proxy into believing a valid WebSocket connection has been established. This means we need to somehow force the backend web server to reply to our upgrade request with a fake one-on-one switching protocols response without actually upgrading the connection in the backend. While we won't be able to do this for all applications, if our target has some vulnerability that allows us to proxy requests back to a server we control as attackers, we might be able to inject the one-on-one switching protocols response to an arbitrary request. In these special cases, we should be able to smuggle requests through a fake WebSocket connection. Leveraging SSRF. In this task application, we will take advantage of an SSRF vulnerability to simulate a fake WebSocket upgrade. After a quick inspection, we can see that the application allows us to test the status of a URL. Each time we input a URL, the server will make a request to the following URL with a check URL parameter and return a status code from the corresponding response. So if we try this URL and inspect in the network tab, we're going to find the 404 status code right here, which will be displayed on the front end right here. We can use the netcat in our attack box to check if we can direct a request to ourselves. We should get a response similar to something like this. This means that we can successfully use the SSRF vulnerability to influence the response of the backend server. All we need to do is to spin up a web server that returns a 101 status, allowing us to fake a WebSocket upgrade. And to do that, we have a little Python script right here to set up a server on our target machine, on our attacking machine, which will respond a 101 switching protocol. Here is going to be our payload. Now, make sure that when you use this payload, this is going to be your attack box IP address. The payload is going to be the same. We use this one, and then the smuggle request looks exactly the same as the previous task. First, let's make sure that we can actually get a request from the server application. Over here, I'm going to turn up the burp intercept. It's going to on 8002. And our IP address is 1067, 76, and 199. On port 5555. Okay, methods not allowed. Let's try again. Here we go. We get the connection request. So that's expected. So now we're going to set up listener. This is going to be Python code. Copy this one. We run this one on port 5555. And over here, we're going to intercept the traffic this time. Turn on burp intercept. Send it. We are looking for this one. So everything looks correct. Let's just copy this one. Put it here. Now make sure that you have 2 new lines at the end. And send a request. Okay, looks like there's something wrong. Let's double check everything. So this one is correct. Check URL server. Okay, request. We forgot to include the WebSocket headers right here to request an upgrade, which is why it's failing. So what I'm going to do is copy these headers and put it here. We've already got this one, so we're going to delete it. Now this one should work. Content length. We send it. Looks like this one's not working either. Let's try the whole payload right here. First, we have to modify this one. 10.67.76.199. Oh, extra. Now we have 2 extra new lines. Also, I think I forgot to disable this one, so I just want to make sure I disable that. And send. Still nothing. Remember that this one is not WebSocket endpoint. We're just manipulating both the request and response that the proxy gets to make it believe that this is a real WebSocket. This means that the proxy will turn on the second request in our payload as if it were a part of the WebSocket connection, but the backend will just process the request as an HTTP since there's no WebSocket in reality. Here we go, we got a flag. Conclusion. In this room, we've shown you 2 ways attackers can abuse the WebSockets upgrade mechanism to smuggle requests through a vulnerable proxy. While this attack only works for specific setups, it's worth exploring since WebSockets adoptions will likely increase in time. So that's it for the room today. If you have any questions, feel free to reach out to me. Again, for this lab, it takes several times to try. If you fail on the first try, don't get discouraged. Try again, play around with the payload and the headers. Eventually you get a flag. Thank you again for watching, and I'll see you next time. See you. Bye.